Hello everyone and welcome to my final presentation for stellar astrophysics. I have chosen the topic of SOHO, and I have titled my presentation Staring at the Sun, because that is exactly what SOHO does, although I wouldn't recommend that you try that at home. So, we're going to split this presentation into three parts. Part one is going to be the history and background of SOHO before we dive into exactly what it does. So let's get started. First off, SOHO stands for Solar and Heliospheric Observatory. It's a bit of a clunky acronym in my opinion, Solar and Heliospheric Observatory, but I've come to... Oh, and that's a picture of that's a computer-generated picture of the satellite generated by NASA on the right. But yeah, I found that acronym to be kind of clunky, but I've noticed that in the realm of astrophysics, a lot of acronyms are kind of a stretch. Anyway, let's get serious. So, the background of SOHO. It is a joint NASA and European Space Agency research mission. To the right, you see the mission patch for the European Space Agency. It's been in use since May of 2015, and the spacecraft was designed with the following scientific objectives. So, they want to investigate and study the outer atmosphere of the Sun, more specifically the three outer layers of from furthest in to furthest out, the chromosphere, the solar transition region, and the corona. They also want to observe and monitor the solar wind in the spacecraft's immediate vicinity, so just the solar wind that's passing by the spacecraft. They're observing that in real time. And then they want to examine and investigate the interior structure of the Sun. So, a little bit of history. SOHO is actually pretty old for a satellite. It was launched on an Atlas II rocket on December 2nd, 1995, from Pad 39A at Kennedy Space Center in Cape Canaveral, Florida. And that is exactly what you're seeing on the right of your screen. It began operation in May of the following year, when it reached its parking orbit, which we will talk about in the next slide. And the mission was initially meant to last 2 years, but the spacecraft has now been in mostly continuous operation for over 25 years. And I say mostly continuous because in 1998, just a couple years into its operation, actually 2 years and 1 month, the mission was nearly a total loss. They were performing some gyroscopic calibrations and maneuvers, and they completely lost control of the spacecraft. It was no longer pointing at the Sun, and it was spinning, completely out of control. A few hours later, they lost communication with it entirely. When they were finally able to regain communication with it, only one of the gyroscopes was still working. They were able to use that to reorient it, get it pointed at the Sun again, get it back in its proper orbit, or proper telemetry. But later that year, in December, that last gyroscope also failed. So, the European Space Agency was forced to develop a method for the spacecraft to operate without a gyroscope. And as such, it became the first 3-axis stabilized spacecraft in history to do so when they put this new method into effect on February 1st, 1999. It's actually quite interesting. It uses one of its flywheels as a sort of virtual gyroscope. I don't fully understand how that works, but it's insane that they were able to figure that out and save the entire mission. And if it weren't for that, it would no longer be in use today. Oh, I guess I gotta... Okay, there we go. Operation. So the spacecraft, now we're getting into the orbit. The spacecraft operates in a halo orbit around L1, which is the Sun-Earth Lagrange point number 1. And so this is the point in space where an object at that point will have an equal orbital period for the Sun and the Earth. Now, it can't actually just sit in L1. If it were to do that, there would be a lot of radio interference between it and the Sun, so we'd have a hard time communicating with it. And also, just actually sitting at L1 isn't a stable orbit. So instead, as you can see in the animation to the right, it orbits around the Lagrange point. And you can see that's its exact movement from its launch or its deployment from the rocket until December of 2018. So normally the spacecraft continuously communicates, and I just mean under normal operation, the spacecraft communicates continuously with Earth at a state-of-the-art rate of 200 kilobits per second. which is not fast by today's standards. But in 1995, it was several times faster than the average high-speed internet, or than the average internet connection. So, quite impressive for the time. It reports twice daily for images of the sun, just standard images under different wavelengths, and near real time, actually, for images of the sun's outer atmosphere. And these observations can actually be used to predict coronal mass ejections, which we will see later. Actually, quite soon, because part 2 is instruments. So, I'm going to go through the instruments. I've organized them by the scientific goal of the spacecraft that they contribute towards. And we don't have time to review all of them. We're just going to go through the most important, or the ones that I think are the most interesting, the easiest to understand, and the most relevant. So, first off, the first scientific goal is studying the sun's outer atmosphere. And the first of the 2 instruments we're going to look at in depth are CDS. So CDS stands for Coronal Diagnostic Spectrometer, and this detector is sensitive to extreme UV radiation. And so it's able to provide information on the temperature, density, elemental composition, and flows of the ionized gases within the sun's magnetosphere. The image you see to your right is the atmospheric structure above a sunspot. And so you can see the temperature change, and it was obtained from CDS and in combination with a few other SOHO instruments. Now, the other one that I think is quite cool is LASCO. This stands for, as another one of those clunky acronyms, Large Angle and Spectrometric Coronagraph. So the Large Angle and Spectrometric, that's got to be how you say that, coronagraph. It consists of 3 specialized telescopes, also known as coronagraphs, referred to as C1, C2, and C3, and each telescope has what is known as an occulter disk, and this blocks the glare from the sun directly and basically simulates a solar eclipse. And if you've ever had the privilege of witnessing a solar eclipse, you know what the corona looks like, and that's exactly what this does. It blocks out just the body of the sun, so you can see the corona. It actually blocks out more than that. The white circle in the center of that occulter disk is the actual size of the sun. And so this is an image showing you from the C3 lens sort of what a LASCO image looks like. So if you see this later in the presentation, all of these are from LASCO. And actually, I have a few more images from LASCO. This one's super cool. You can see Mercury, Venus, Jupiter, and Saturn, as well as the Pleiades to the top left, in the middle of a coronal mass ejection. So that's pretty cool. And now here's another one from the C2 telescope. And it's just a massive coronal mass ejection in the upper left, as you can see. And now some other instruments that help study the sun's outer atmosphere that we don't have time to get into in this presentation are EIT, SUMER, SWAN, and UVCS. Actually, SWAN we will get to, but for a different scientific goal, and that is this next one. Instruments for observing the solar wind. So first we have CELIAS. This stands for Charge Element and Isotope Analysis System. So what this does is it directly detects the solar wind that's coming into contact with the spacecraft. And in doing so, it's able to collect data on the density and composition of the wind's composite particles. And to your right, you see an image of a coronal mass ejection. The left is a composite of an EIT image, which just takes optical images of the sun. And that's superimposed on top of a LASCO image, so you can see both the sun and the corona. You can see the coronal mass ejection on the right coming into contact with Earth's magnetosphere there as well, and you can see how it is mostly deflected, but not entirely, because of just the sheer volume that is coming into contact. Alright, now here's the second instrument, SWAN, like I mentioned earlier. This one is fascinating. It stands for Solar Wind Anisotropies, I believe is how you pronounce that. Or Solar Wind Anisotropies. So it's the only instrument on board SOHO which faces away from the sun. I found that to be very interesting. And what it does is it searches for alien hydrogen atoms. This is basically interstellar medium that's passing through the solar system, and the solar wind ionizes it, and when those electrons, so the electron gets decoupled from the nucleus, when it rejoins, we know how it works. It drops an energy level, it emits a specific ultraviolet wavelength. So that can be detected, and that is what SWAN is looking at. But it's counterintuitive a little bit, because what it's actually looking for is the lack of ultraviolet radiation, because that means that the solar wind is ionizing a lot of the ISM, because then the electrons are decoupling, and they only emit radiation when they rejoin the atom. So this level of UV can be detected. It's an inverse relation. The less UV detected, the more intense the solar wind is at that time. Now, moving on to instruments for studying the interior of the sun. First one is GOLF. Now this one is quite complicated, difficult for me to wrap my head around, honestly, but it stands for Global Oscillations at Low Frequencies. Basically, it isolates the light that's coming towards the spacecraft to just a 1.7 nanometer band of light from the sun that corresponds with the sodium delta lines. And then in the P1 polarizer and the QP2 quarter wave plate, I believe, it is able to circularly polarize that light. And in doing this, you can determine the solar velocity, which gives insight into the state of the sun's core. And the image you see to the right is just a schematic of how that works. It's quite impressive, actually. Finally, and there's no image for this one, MDI, which stands for the Michelson Doppler Imager. And this one, unfortunately, is no longer in service. Well, not unfortunately. It was superseded by a better and more robust instrument on a different spacecraft called the Solar Dynamics Observatory. But yes, it used to observe the velocity and magnetic fields in the photosphere, and it provided insight into the state of the sun's convection zone. But once about a year after the Solar Dynamics Observatory spacecraft had become active, they permanently shut down this instrument. Alright, now a fun bonus, comet detection. This is a really cool consequence of SOHO's position. Because of specifically the LASCO instrument, because it blocks the glare of the sun to simulate solar eclipses, this instrument has inadvertently facilitated the discovery of a large number of comets. And today, approximately half of all known comets have been discovered by SOHO. In fact, just last year on June 15th, a volunteer spotted a previously unknown comet in a LASCO C3 image, which you see to your right, marking SOHO's 4,000th comet discovery. And in the little blown up portion of the image, it's the crosshair on the top, the dimmer of the two comets, is the 4,000th comet discovered by SOHO. Alright, and as a little bonus, here is today's solar images. I got them straight off of NASA's website. This is the most recent data relayed from SOHO, so you can see it's still transmitting data at all times. Alright, now just a quick recap. Main points. So SOHO has provided invaluable insight into the sun's structure and inner workings. The spacecraft serves as a real-time monitor of solar weather and allows us to prepare accordingly here on Earth. And finally, the extraterrestrial observatory is really a groundbreaking technological feat, which has continued operation for more than 12 times the length of its original mission span. And here are my references, and thank you for listening.